We started off last time talking about this 0D lump capacitance problem, and the purpose of this discussion was for us to come up with a way of modeling this using Laplace transforms. We have this body that has some generation that's a function of time, and so we're going through and we're developing a differential equation. This differential equation is always the same, regardless of what we're doing. And then once we get it to this point with our initial condition, then we can apply the Laplace steps to this. So we were doing that. We came up with our Laplace transform by by applying all the rules that we found in the table, and we ended up with an expression, a direct translation of the time expression into an S-domain expression here. So this is our equation transformed into the Laplace domain. Then the job is we still need to solve for t hat. We're trying to come up with a temperature profile. The whole point of doing this is to come up with a relationship of stuff on the right-hand side and then just temperature on the left-hand side. So we're almost there with this. It just is an algebraic equation. And that's the good part about this, is you went through from an ODE down to an algebraic equation that we can solve. And we started doing that solution. Here, we grouped together the t hat stuff, and then we just solved explicitly. So this is the solution for the Laplace domain. Right? We have a temperature-only solution in the Laplace domain. Now we need to bring it back to the time domain. So that's what we're going to do next. So we've got our solution. Well, if you look at this, I guess what you see is on the right-hand side, there's at least 3 terms, and then you have this denominator. So in order to simplify this out, where we can get stuff that we can take the inverse Laplace, let's actually multiply through by the denominator and get things kind of in a consistent form there. So if we do that, we end up with t hat is equal to, the first term would be t infinity over tau s plus 1 over tau. And then the second term would be g dot triple prime over rho c s plus 1 over a times s plus 1 over tau. And then the third term is just t infinity over s plus 1 over tau. So we're just doing algebra to get us to a point where we can see what to do next. And we're kind of there now, right? If you remember back to the method of partial fractions, we have each of these terms can be treated separately. And we have stuff where it's like these repeated or terms that are multiplying each other in the denominator. So I told you this is where we'd end up, and in fact, we do end up here, so I wasn't lying. So what you need to do is find a way to break this up now where we have like one term that's just something over s, another term that's just something over s plus a constant, and do that for each of these terms. On the last term, it turns out, if you look at this basically already exists in a table. So we could look at, we have some constant over s plus a constant. And that was, if you have to take my word for it, but that was just t infinity exponential of minus t over tau. So if I were to take the inverse Laplace of the last term, I get that. The other stuff we have to do more with, right? We have to do more operations to get that to something invertible. So how should we proceed here? Let's take the first term, this one here, and start breaking this up. So the first term is t infinity over tau s plus 1 over tau. And then let's assume that that's going to be equal to c1 over s plus c2 over s plus 1 over tau. Right. And just note, when I'm writing the c1 and c2, I'm sort of neglecting the fact that I have t infinity over tau. That all comes out in the procedure for solving for the unknown constants. So we just say it's whatever the constant is over the important term, which is s, or s plus 1 over tau. So if we do that and then proceed with the method we're multiplying here everything by the denominator on the left, which is tau s plus 1 over tau. And then let's see, we have t infinity is equal to c1 tau s plus 1 over tau plus c2 tau s. Then we group like terms. So let's take everything that's multiplying s to the 0th power. So on the left, that would be t infinity, so t infinity, and then on the right, that would be c1 times tau over tau. So that would just be tau. Okay, so that would be t infinity is equal to c1. Then let's take everything that is s to the 1st power, and that is just 0 is equal to c1 tau plus c2 tau. Okay? That's just telling us what c1 is equal to minus c2. So we've got our solution here for this term. We can go back and write this in a consolidated form. I've kind of run out of room, but let me just write up here in this area. So the result of this is this term is broken into t infinity over s minus t infinity over s plus 1 over tau. Right? So that's our second term equivalent. Does that make sense? We're just taking, sorry, what did I say second? First term. First term equivalent. This equivalent is that. And that we can invert through tables or whatever. Okay? Questions on that? Just algebra. Well, all right, moving on to the next term. Where are we? So we have the first term and the last term kind of broken out. Well, we know what the inverse is for the last term, so that's already in t. We'll hold on to that. We're not going to do anything with that yet. We have our first term. We could do a similar thing for the middle term. I'll go through it quickly because I think at this point it's pretty obvious what we're doing. But going through this, we would say what g dot triple prime over rho c times s plus 1 over a times s plus 1 over tau is equal to c3, we'll call it, over s plus 1 over a plus c4 over s plus 1 over tau. So again, we need to find the c3 and c4 that make an equivalent statement here. Multiply it through by the denominator, and then we end up with the following expression. G dot triple prime is equal to c3 rho c s plus 1 over tau plus c4 rho c s plus 1 over a. So s to the 0th power is going to be g dot triple prime equals c3 rho c over tau plus c4 rho c over tau. Oh, sorry, rho c over a, I think. Rho c over a. So that's s to the 0th power. You can double check that I did that right. And then s to the 1st power is 0 equals c3 rho c plus c4 rho c. We could go back, do the algebra, solve for this. I won't walk through the steps, but I'll just give you the answer here. So it would be, where do we go? So let me just write this up here. So C3 ends up being G dot triple prime times tau times A over C rho A minus tau. And C4 is just minus C3, right? Same thing, but with a negative. first thing is. Okay, so we have this equivalent now. Again, you look at this, this is, these are all constants, right? So we're okay there. And then the constants are just going over this stuff that we know how to invert. S plus some constant. So we're all, we're pretty much set then having an expression that we can just piece by piece do the inverse Laplace. Okay, let's see. So where to go with this? So if we look at this, let's write everything out, and then we'll see how it kind of wraps up. So t hat is now bringing everything together, would be t infinity over s minus t infinity over s plus 1 over tau, plus, I'm not going to write it about C3, right? It's that group that we just solved for. C3 over s plus 1 over a plus C4 over s plus 1 over tau, plus the last term was t infinity over s plus 1 over tau. Right, that's just bringing everything back together. If you look at this, we have t infinity over s plus 1 over tau minus t infinity over s plus 1 over tau plus there, so that actually cancels out. So our last term, even though we know how to invert it, doesn't matter, right? We don't actually need it. Then we're just left with these three things we need to do the inverse. And it's straightforward to do that. So this yields, oh man, I need more room. So this yields in the very bottom here, t as a function of time is equal to a constant over s inverted. If you look at the table, it's just that constant. So it's t infinity plus these two terms. If you look at the inverse there, that's going to be some exponential thing, right? So it looks like what, C3 exponential of minus t over a plus C4 exponential of minus t over tau. That's our answer, the answer in time. And again, remember, C3 and C4 are known. These are not unknown constants. These are known based on our solution. So you can see now that the Laplace transform gives us the ability to go work in an easy domain. And then as long as we can get back to time, we're set. Any questions on this?
Is there an inverse Laplace operator?
That's a good question. I would assume there is. I guess I don't know how you'd write that.
Maybe just the brackets and minus 1.
Yeah, maybe. I don't know. That's a good question. I've never thought about that, but I guess you just do it. I'll look into that. Any other questions? Okay, let's look at the ease implementation of this. And the point of doing this is just to make sure that we know that Laplace matches our answer that we got before. This is all the information that we're given in the problem. We, I guess, could compute things like the BO number and the time constant, which we've done. If you go through and do the partial fraction expansion, you get this system of equations that help you solve for the unknown constants. And then down here we have our first solution. This is the analytical solution that you can get by doing just regular like separation of variables type thing. Although for this is just in time, right? So this would just be solving the ODE for time. We don't need separation of variables, we only have time. So this is the analytical solution. It looks similar, right? Same type of thing. Let's just look at that and see how it plots out. So that I've already done. If we run this table for time, we would see, where did it, oops. We would see this solution here. And so that's our analytical solution. Then the next thing is let's look at how this is actually solved in Maple, and then we'll do the Laplace and bring it back here. So in Maple, this is how you go about doing kind of the same thing that we did. We're going to restart, load our library, and then we're putting in the ODE in time. Next is, this should all line up. ODE in time, this is what you would have derived from your own control volume analysis. So next we're going to take the Laplace. So that's using this Laplace function. And then this is what we get out. So this should match what we did manually for this problem. There's kind of some points to make, though. So the first point to make is this thing here. Right? This is my temperature function evaluated at time equals 0. That's my initial condition. So if you remember the Laplace transform, we're doing S times the Laplace, right? S times T hat of S minus T initial. So T initial, we have to put that in. We would probably want to do that. I guess I've done that down here. Before I do that, I don't want to carry through the entire solution with this function, this kind of longhand representation of Laplace. So I'm going to say wherever this thing appears, I just want to sub it out and call it something else. I'm just going to call it T of S. You could call it T hat of S or whatever you want to do. But you need to denote in some way that it is functionally dependent on S. So we'll just call this T of S, and then it's not carrying around that thing everywhere. So we do that. Our solution looks like this. Now we need to get rid of our initial condition. So we do that by substituting T infinity for T is 0. And now this should be what we need to solve algebraically, which we do here. And the algebraic solution is equivalent to what we did by hand. We went through, and I said, you might not be able to take the Laplace. This is such an easy problem. This is such a straightforward problem. Maple can, in fact, do the inverse, so don't get mad at me. But what you have is a kind of this complex denominator and all those terms that come along, and then you just need to take the Laplace. But I guess you'll have to believe me that there are situations where it won't work. So we'll take the inverse Laplace here, and we see this is the solution. So it should look pretty similar. We would want to convince ourselves that it is the same by plotting it in ease or in Python or whatever. But you see that there's an exponential to time over tau. There's an exponential to time over a. There's some constants that go with it, and then there's a T infinity that appears. So it looks, pretty similar. Any questions on the Maple part of it? Okay. Let's look back at the ease. Okay, so here I've taken the Maple solution and just copy and paste it in here. We have our time. We have all the same stuff that we had, and I just want to prove that it's the same solution. So go to my lookup table. We've got the Maple solution here, the analytical solution here. I can run this and plot both of them, and I did that already. So here you see that the manual solution or analytical solution is plotted in blue, and then the dots are the Maple solution, and it matches. So no big surprise, right? But it's kind of interesting. Like you get the result, and you kind of just take a completely different approach. So it gives you confidence in your answer if that happens. So that's the way that we would approach the 0D lump capacitance. Again, most of the problems that you're going to solve in 0D lump capacitance, you're not going to need to do Laplace for. I mean, you might use it for a weird boundary condition or something like that. But most of the time, those are straightforward enough. You don't need to use Laplace. What we really wanted to do and why we're going to this effort is to do 1D problems.